Good afternoon. We are starting our last session of today's meeting. And our first speaker will be Robert Laxdal from Triumph, and he will talk about sustainability in ICHEP, detectors, accelerators, and computing. Robert, please.
Thank you, Mr. Chairman. Do I have sound? Do I? Okay, very good. So thanks to the organizers for putting this important topic on the agenda. I want to start just by looking at a couple of statements from important panels. So in 2020, the European Strategy of Particle Physics stated that the environment impact of particle physics activities should continue to be carefully studied and minimized. A detailed plan for the minimization of environmental impact and for the saving and reuse of energy should be part of the approval process for any major project. And then from P5 report, a commitment to sustainability is a high priority for particle physics activities. This includes energy and carbon management, energy efficiency and savings, and environmental impact. It concerns present and future accelerators, as well as testing and computing facilities. And why is it important? It's really because human life on Earth, as we know it, is endangered by the unsustainable exploitation of many of the natural resources. One of the most urgent issues is CO2 from burning fossil fuels that accumulates in the atmosphere, and it is the CO2 in the atmosphere that is the primary determinant of the Earth's average surface temperature. And certainly we all see that from 1980, there's been a steady rise of the surface temperature on Earth. Present large high-energy physics facilities have a significant carbon footprint. Consumption of electrical energy, greenhouse gases from detectors, heating of buildings, procurements, travel and commuting, and waste. The present operation and future accelerator projects need justification not just in terms of scientific output versus effort, cost and resources, but also versus the overall electricity consumption and carbon footprint. The present global energy production is dominated by fossil fuels. You can see on this curve, even with all of our efforts to date, it's still largely associated with fossil fuel consumption. And to wean ourselves from fossil fuel will require a dramatic reduction that will create an energy gap. This will require a rapid rise of climate-neutral power generation. Energy costs will certainly rise, and it requires energy savings and recuperation in our operation. Rising costs and enhanced scrutiny will challenge high-energy physics accelerators, experiments, and data analysis centers, both present and in the future. So first, let me go over some definitions. The carbon footprint is the amount of greenhouse gases expressed as CO2 equivalents that are generated either directly or indirectly from a specific activity. The global warming potential is a measure of how much energy the emissions of a kilogram of gas will absorb over a given period of time relative to the emissions of 1 kilogram of carbon dioxide. And here's a couple of examples where over 100 years, the global warming potential of methane is 21 times carbon dioxide, and of SF6 is 23,000 times carbon dioxide. The carbon intensity is the carbon footprint embodied in a process. It's given either by a kilogram of CO2 equivalent per kilogram of material or kilogram CO2 equivalent per kilowatt hour for energy, and depends on the method of production So, for instance, aluminum, depending on where it's produced, either in Europe, 7 kilograms per kilogram, or in China, 20 kilograms per kilogram. The source does matter somewhat. For concrete, a lot of our projects involve tunneling and building infrastructure, 0.1 to 0.2 kilogram per kilogram of concrete. We are large power consumers. Here you can see a few examples, but just picking on the Large Hadron Collider, 120 megawatts, and in the future, estimates for FCC-EE is 282 megawatts. And compare that with large infrastructures associated with societal power production. The carbon intensity depends on the process used to produce the energy and is improving with time. You can see from the UK the carbon intensity, and in Canada, as more green energy is brought online. But you can see a difference in the source of the power depending on what the power is driven by. So the French power, with mainly nuclear, is the lowest of these three examples. Regardless of the power source, laboratories should aggressively seek ways to reduce power consumption as the globe transitions to low-carbon solutions. We require community actions. So simplistically, reduce the energy consumption per person by increasing energy efficiency and modifying culture while transitioning away from carbon fuel sources. An interesting example is the 2,000 watt society in Switzerland, where the numerical goal for primary power consumption per person is 2 kilowatts annually, or 2 kilowatts. Just to compare that with Europe presently is 4.4 kilowatts, and in US, 9 kilowatts. So this sets a target for the Swiss citizens, and it's a good example for the world. The accelerator community needs to evolve to more efficient technologies and support R&D to reduce total energy consumption in line with the public. This requires a change in culture in our culture. We need to focus on energy efficiency with the same priority as achieving higher performance. Like the 2,000 watt society idea, a numerical goal for energy consumption of accelerator-based user facilities could be beneficial. We could set, for example, maximum power consumption per user, say 5 kilowatts per user. Just as a point of example, the LXC right now with 12,000 users uses 10 kilowatt per user. RIC uses 25 kilowatt per user, whereas light sources are already under the 5 kilowatt at 3 kilowatt per user. At any rate, each lab should set interim targets with budgets and resources to reduce their yearly consumption in steady progress. The accelerator community has engaged in R&D to reduce energy consumption. We're trying to make efficiency gains from improved technology or energy recovery. Here's a few examples. We can develop more efficient helium refrigerators. We can develop and are developing superconducting technologies. High-temperature conductors can reduce power in DC applications. New SRF materials can reduce cryogenic power in accelerator RF acceleration. We can deploy more permanent magnets, and we can develop more compact accelerators to reduce construction footprint, like the Muon Collider or Wakefield accelerators. We can use energy recovery to make our acceleration more efficient and develop energy recovery for our pulse systems. As well, we can recover process heat using heat pump technology. Beyond electricity consumption, HEP facilities produce considerable CO2 emissions. Methodologies are being developed to help better compare and guide facilities in operation. We group our facilities into 3 areas: particle accelerators, large particle detectors, and high-performance computing. And then each area we look at in terms of 3 common categories or scopes. Scope 1 is emissions from a source that an organization owns. For instance, the organization's cars or the leaked gases from the detectors. Scope 2 is emissions associated with energy purchased and used by the organization, the power from our grids that is produced by gas burning in power stations. And Scope 3 is everything else. It's emissions associated with the manufacture and disposal of products that are used by the organization, or the emission from commuting or business travel. Large computer data centers are power hungry in the computation and the cooling. Across all sectors, data centers and computing already contribute approximately 2 to 4% of global greenhouse gas emissions. And that fraction is only predicted to grow in the next 10 years. The power usage effectiveness and the water usage effectiveness are key performance indicators for data center efficiency. As mitigations, we should continually and are continually upgrading software for more efficient algorithms, set targets for our power usage and water usage in a continuous improvement cycle, promote R&D towards efficient computer hardware, coordinate power loads with their electricity suppliers to reduce consumption during peak hours. implement plans for waste heat recovery in the design phase of new computing centers, and provide information on the greenhouse gas intensity of the computation in a standardized, transparent format to help gauge progress. Direct greenhouse gases from our particle detectors release significant quantities with high global warming potential, 1,000 to 10,000 times CO2, namely in SF6, PFC, and HFC. Escaping gas presents a serious risk for adding to a facility's yearly carbon footprint. It's, for example, responsible for 40% of CERN's total annual carbon footprint in 2022. European regulations will target research institutes more stringently in the future, and this will significantly impact cost and availability of these gases. The mitigations here are to reduce the yearly greenhouse gas consumption of operating systems and develop new systems for better retention, and to research new environmentally friendly gas mixtures. HEP facilities require significant procurements to maintain and develop scientific infrastructure and support on-site activities. Each procurement is associated with a certain carbon footprint required to produce the raw material or part, and can be a significant fraction of the facility's yearly output. The mitigations, straightforward: reduce, reuse, recycle. Also to adapt and adopt sustainable procurement policies. Consider the full life cycle of the procurement, the carbon cost of production, and the carbon footprint of operation and disposal, and not just the capital cost. And develop a vendor database in collaboration with other labs that rewards good practice. HEP participants tend to travel frequently for collaboration, and travel has got a significant carbon footprint. One transatlantic flight per person is associated with 1 ton CO2 equivalent. Domestic flights, depending on the distance, of course, between 0.2 and 0.4. And commuting just to the lab and back on a weekly basis, if you have a gas car, at 100 kilometers a week, produces 1 ton CO2 equivalent annually. Mitigations here are to provide incentives for public transport and environmentally friendly transport, incentivize the reduction of business air travel, set personal and lab goals while considering inclusion, and as a community to develop better hybrid approaches to meetings. So as two examples of the global, as the GWP, CERN in 2022 had a total GWP of 350 kiloton CO2 equivalent. And to put that in context, assuming 12,000 users, this corresponds to 30 tons CO2 equivalent per user, or roughly 5 times the average individual annual carbon footprint in Europe. More than 78% of CERN's Scope 1 emissions are due to detector gases. CERN's goal here is to reduce the Scope 1 CO2 equivalent emissions by 28% by the end of this year. More than 90% of Scope 3 are from procurements when you consider the full life cycle of the products. And just moving to another example, STFC in 2022 had a total GWP of 29 kilotons CO2 equivalent. This corresponds to 17 tons CO2 equivalent per staff member, or 4 times the national average. So in general, our society has a high CO2 footprint compared to the average society. Just quickly looking at the future, these are a number of projects that are being discussed moving forward, large projects. Here, for new project proposals, a full life cycle analysis methodology is being developed. The goal is to enhance scrutiny on projects beyond cost and effort. Such analysis estimates the total energy and carbon footprints over the full life cycle and should play an important role, and maybe a defining role, in selecting the next project. The life cycle analysis includes both the construction and operation phase with CO2 emission and energy consumed per ton of concrete, steel, and aluminum, as well as CO2 emission during operation and decommissioning. And already some large collider proposals, the FCC, ILC, CLIC, and C3 have already prepared such life cycle analysis. In the interest of time, let me just move to my summary. The present large HEP facilities have a significant carbon footprint from consumption of electrical energy for accelerators and data centers, greenhouse gases from detectors, heating of buildings, procurements, travel, commuting, and waste. The worldwide climate emergency requires everybody to take urgent action, including the HEP community. Future accelerator projects will need to minimize resource use, especially energy consumption, and reduce CO2 emissions throughout their life cycle from construction, operation to decommissioning. And some proposed actions support the completion of comparative life cycle analysis of total energy and carbon footprint for all accelerator projects, support R&D of increased energy efficiency and reduced carbon emissions with a priority at least as high as performance and cost reduction, advocate low-impact commuting and remote or hybrid meetings to reduce air travel in our community, reward industrial partners who exemplify best practice in sustainability, consider carbon cost in addition to capital cost in procurement decisions, establish and report key performance indicators regularly and transparently with concrete goal setting, and finally, consider a community-based approach to neighborhood energy efficiency through transformation of waste heat to energy. Thanks for your attention.
Thank you, Robert. Very interesting talk with a lot of information and specific proposals. So please raise your hand and ask Robert. Okay. Okay, please. Yes, Robert.
Yeah, thank you very much. I'm sorry if the following question is going to sound provocative, but I assure you it's not. While we do all these efforts to do this, the rest of the society does not, and because it is a political issue. So I wonder whether, as a particle physics community, we should also advocate not to vote certain parties that deny climate change.
Sorry, what was the last part of the question?
Sorry, the only part of the question is really if, as a particle physics community, we should advocate, and I say we should, not to vote certain parties which are openly deniers of climate change.
Okay, so that's, yeah, that's too political for me, but I would say I think what we can be is purveyors of the truth. And so wherever we have the opportunity to present facts, and that we should do so. But we should also lead by example. So, you know, there could be the case that governments or power distributors raise the prices and we have to react to that. But we could, I think as a community, we should be proactive and basically, you know, be good citizens of the world, make our processes efficient and look forward, make our procurements efficient, travel less, do what we can in order to avert this crisis, because everybody has to take their part.
Any other questions? Yes, please.
Yeah, but in your discussion, you really didn't say what would be a good goal for our field to put as our objective. You talked about that we're trying to reduce it and whatever, but you didn't really go into, I mean, if we're going to lead, then we should be able to formulate a good reason for why we have a particular number for our lab, let's say. And I didn't get that from your discussion. I got that we should try to get to, you know, to try to make such a goal, but I didn't see any number. Maybe I missed it. Maybe you have one.
No. I mean, it's an excellent point, but I think the first thing we have to acknowledge is that we use more than the average person in our processes. We are power hungry. We have a lot of greenhouse gas emissions. So I think the first thing we have to do is look ourselves in the mirror and ask ourselves, where can we get to? So I think the answer is there's no simple fix. There's continuous improvement. So I think each lab should keep, you know, accurate, transparent records that they divulge annually. and set honest targets with resources and people behind them in order to, in order to meet those numbers.
Thank you, Robert, for that. One more question. Yes, over there, please.
Yeah, thanks for this presentation. And in a way, the first step we are doing, we are collecting the numbers, and now we have to take actions. Some of it is more straightforward than others. Nothing is going to be easy, but each one of us has personal responsibility, and we could, as you said, look in the mirror. Is this trade necessary, just as an example? But how are we going about procurement? I mean, it's not only at CERN. How can I convince my university not just buy computers from the cheapest vendor, but also look at where the stuff is made and maybe even not have principles of replacing everything every 4 years?
Yeah, no, that's an excellent question, but I think that's something we can do as a community. So it's not just one university that can get all the data from all the vendors in the world and know what the carbon footprint is of this computer versus that computer. But I think as a community, as long as we share information and recognize first that it's important to have that information, that we can begin to develop databases. And I think we have to get to the point where we don't just look at the capital cost, we look at the carbon cost. And that's something that, you know, as a dialogue also with our funding agencies, in order to support such initiatives.
Okay, let's thank Robert for a very nice presentation and wonderful answers on the questions. And I am transmitting my...
Thank you, Dimitri. Now I'm pleased to welcome to the stage David Rohr to speak on the topic of computing and software.
Okay, thanks. I'd like to thank the organizers for giving me this opportunity to speak about software and computing on behalf of the 4 LHC experiments. And I want to thank you for being here. And I want to thank all the people from all the experiments that sent me all the comments and the remarks and the material. So I cannot name them all, but thanks to all of them. And before I start, I want to mention that there was a very similar talk by another David Schoop, at LHCP 2 months ago. And he was talking more about analysis and simulation. I will talk a bit more about reconstruction, so that will be complementary. So if you're interested, please have a look. Here is the link. And I want to say, since this is a summary talk, I will not always mention when there are references to other talks, because there will be plenty. They will all be in purple color, like here. So whenever you see purple color, you can check the PDF and click on the link, and you will have that. So without further ado, the challenge of the computing for us is basically shown in the figures here. So irrespective of whether we are at ALICE, so here you see an illustration of a time frame with continuous data, and ALICE has overlapping collisions due to the drift detector that cannot be disentangled. Or if it's another experiment like Atlas here, where we have high pileup and many PE events overlapping, the challenge is always processing data of very high multiplicity at very high rate. And we are now in run 3. So ALICE and LHCb have finished their upgrades. Here we see the interaction rate plot for LHCb. And after the upgrade is before the upgrade, so LHCb is already planning the next upgrade for run 5. ALICE is going in the same direction. So you see another step in the interaction head here. And then, of course, there's the Halloumi upgrade for Atlas and CMS, which will go to even higher interaction rates up to the ultimate pileup of mu equals 200. And this plot here shows the estimated Atlas computing demands for Halloumi, and we can replace the plot with LHCb, and you see the plot is basically the same. So we have to make sure that we can meet these computing demands in the future in order to be able to process the data that we are recording. So now we can answer the question, what can we get from the industry? And this plot shows the performance of Intel and AMD processors in single and double precision floating point over time on a logarithmic scale. And you see it's almost a line, but it's not a perfect line, which means the performance increase is slowing down a bit. It's maybe not fully exponential, but I would say it's still almost exponential. And then we can look at graphics cards instead of processors. And there's kind of a constant gap in between, so graphics card performance is increasing at the same pace as processor performance. So this looks actually promising, and we could think we should leverage these capabilities of the hardware. But there is this very nice slide by Graham from some years ago, which shows that to program these new architectures efficiently, we basically have to consider more aspects, more layers, more particularities. and that makes the programming a bit more complicated, and you need to have more knowledge. And this is in contrast to the fact that we have more and more developers writing more and more code, so we should actually try to simplify the software development. And yeah, it's difficult to find the right compromise here. So this was for the computing so far. Then there's, of course, the storage. And the problem is that the storage capacity is actually growing slower than the compute capacity, which means that we have gotten into a situation where we can process more data than we can store. And if we look at Alice, we see the amount of data Alice is storing in run 3. We see these huge bumps for let rate. And Alice is storing 100 times more events right now than we did in run 2. And we can look at the Atlas computing estimates for high Lumi upgrade, and we see this very steep increase once run 4 starts. So we have to do something here. So there are some efforts. For instance, Atlas and CMS are looking into adapting root error n tuple, which should give some percentage in data size. Then Atlas has this data carousel where they use disks as temporary storage to cache data from tape and making tape a warm storage. So this all decreases the data size, but we really have to look into efficient compression and triggering algorithms to be able to store this data. So this brings me to online computing, and I want to talk particularly about using accelerators in online computing. And the LHC experiments are going in 2 different directions for online computing. So Alice and LHCb, they have basically completely removed the hardware trigger, and they do everything in software. And they also do the full processing on GPUs. And you see an illustration how it works here. So there's actually a 2-phase process. This is the plot for LHCb. Alice looks similar. So it's the first processing here. It goes to a disk buffer, then there's the second processing. A second difference is that Alice is actually not triggering anymore. Alice is only compressing the data and then writing it to storage. LHCb, in contrast, is doing the full trigger basically in the HLT1 on GPUs. So when we look at Atlas and CMS, the rates are way higher because they have the high Lumi upgrade with the higher pileup, so they cannot do away with the trigger. They have the hardware trigger, and they use FPGAs for that. And CMS is using, in addition, GPUs in the high-level trigger farm. Atlas is doing that not yet, but they have support for it in their build system, in their infrastructure already, so they will do something for the high Lumi upgrade, and they will announce next year what exactly they want to do. And I want to mention one particular thing here, and this was also advertised by Maurizio this morning. So there's the scouting stream of CMS, and there's the turbo stream of LHCb, where they actually store additional objects on top of the raw data that they store. And they just stored the HLT objects, which were much smaller, so they can basically provide more statistics to the analyzers for certain use cases that can fit in these streams. Okay. Then I want to talk a bit about the experiments in detail, about the GPU usage. So this is a slide about Alice. The plot here shows different GPU models that were measured by Alice for their performance. Alice is at the moment using roughly 3,000 GPUs in the online computing farm, and each of the GPUs, they have 2 types, replaces either 80 or more CPU cores. And the take-home message here is that without using GPUs in the online farm, Alice would need more than 3,000 servers, each 64 cores, which would be prohibitively expensive. Then we can look at CMS. So CMS has this hybrid farm using CPUs plus GPUs in the high-level trigger, and this plot shows the speed up using from non-GPU version to CPU plus GPU. And we see that, so this shows the time for all the individual processing steps. And when we look, for instance, at the pixels, we see that the pixel time went down significantly because the pixels are offloaded to GPU. Other steps are not improved that much. But if we look overall, then CMS has a speed up of 1.8x using GPUs for the high-level trigger. Then there's LHCb, which I already mentioned, so they do the full HLT1 on GPUs. The driver here was basically a global cost-benefit analysis, checking different GPU models to be used in the HLT1 farm. What basically gives the best performance for the budget they have. And they do the full triggering on GPUs. So they start with the Velo, then they have the upstream tracker, the Sci-Fi, and then also the muons, electrons, and calorimeters, including the primary vertex finding and the full trigger algorithm. Everything runs on GPU end-to-end. So GPUs just output the final trigger decision. And yeah, this plot, similar to what was shown this morning in the LHCb summary, shows the efficiency increase by using this full software approach over the hardware approach that they had in run 2, which is quite impressive. Okay, beyond GPUs, I want to mention also other hardware accelerators. So FPGAs are used by all the experiments. Alice is using, or was using FPGAs for TPC clustering in runs 1 and 2. Now they are only doing iron tail correction and common mode correction for the TPC. Then LHCb is doing clustering for their Velo. Atlas and CMS are using FPGAs for the L1 triggers. There are links to the references here. And there are efforts to use FPGAs also for tracking, for instance, by Atlas. But the FPGA development is complicated and also needs a lot of time, and it was not always successful. So 2 examples here is that, for instance, Alice had to drop the effort to continue doing clustering in Run 3 because just the software was the design was too large, it didn't fit on the FPGA. And also Atlas has dropped the usage or the idea to use associative memory-based tracking with custom ASICs. Okay, so this was for online. Now the question is, where can we use GPUs beyond online processing? And this plot here shows the Alice offline reconstruction time in red, which is less than half of the total CPU time that is burned in the grid. And for example, Atlas has 70% of the time in simulation. So the naive thing would be to use GPUs also in offline reconstruction because the code is similar to online. But if we do this, we affect only a part of the reconstruction. It's still of the processing. It's still a good thing to do it, but it's not sufficient for everything. But yeah, in any case, I want to talk about that, particularly about Alice, but I want to mention that CMS is looking in the same direction. They have offloaded their GPU software to Alpaca, and also Atlas is looking into that, particularly for using grid resources opportunistically. So yeah, the tables here show the relative processing time of the individual steps in the Alice reconstruction. We have online here, and then we have offline PP and offline LED. And the important thing is that online is quite simple because all of the time goes into TPC processing. Therefore, Alice has decided to go with 2 phases. In the first phase, which is called the baseline scenario, they do only what is needed for online, so offloading this to GPU. Of course, it will benefit also offline because there's also significant offline part. Afterwards, in the phase 2, they want to offload the global barrel tracking, which is all these components. So you see a lot of them are green, so that is already done, including the baseline scenario, but this is still work in progress. But once this is finished, Alice will be able to offload all these steps to GPU, which will be 80% of the total compute load, which should result in a speed up of 5 times compared to running CPU only. What they have today is that they can offload 60% in the baseline scenario, which gives a 2.5 times speed up. So this was the theory. So in practice, Alice has split the online farm in 2 partitions, so they can run offline jobs in that partition. They never use online and offline jobs on the same node, and they move the node between the partitions. And they have basically measured different configurations of CPU workflows and GPU workflows to have a fair comparison by just comparing the best GPU version to the best CPU version. And if we do this, we see that with GPUs, they are 2.51 times faster. So this is quite exactly the factor that was predicted by the 2.5 from the offloading the 60%. So this is quite nice. And this is with 2023 software, so the baseline scenario. Since then, there is additional work ongoing to offload more stuff, and there was a talk at LHCP showing that now in 2024, we have 1.5 to 5 times more code offloaded to GPU. Okay, then the question, how much of the software is actually running on the GPU? So this plot here on the left shows all Alice grid jobs, averaging at 120,000 cores in average over time. And the right plot shows the jobs that use GPUs. You see it's fluctuating a lot because the farm is also used for online, particularly here during LED data taking, there are 0 jobs. But if we look at the high load, we have 25,000 cores using GPUs, so this means 20% of the grid resources of Alice were using GPUs at that time. And then the last slide on GPUs, I want to emphasize that there's basically an agreement of all the experiments that none of them want to be vendor locked. So all of them are trying to do some generic programming to be able to switch the supplier of their GPUs. So CMS has ported their stuff to Alpaca. Atlas is looking into Alpaca as well. Alice has this framework which is shown here, which was developed before Alpaca, so they couldn't look into Alpaca. And okay, LHCb is actually using native CUDA for their Elm framework, but they are looking into porting it to AMD HIP and Intel One API. Okay, so going from GPUs to frameworks, and here one of the most important developments recently was the multi-threading for Atlas for Run 3. So here we see the advantage in memory that they gain by running multi-threaded code, and CMS has done the same, but earlier already for Run 2. Alice is also doing the same, so at the moment Alice can only do multi-threading inside algorithms, but they are working to have framework support for Run 3, but yeah, it's work in progress. And if I can say, so my personal wish list here would actually be to have seamless switching between multi-threading and multi-processing on the framework level so that you just can configure it. So you could run for production multi-threaded, but for debugging you would have the multi-processing. Another topic is the scheduling for many core architectures, and this is particularly a problem for Alice, and I have some details in the backup. This is when you want to load all the cores, you want to have many timeframes, events, whatever data in flight, but you also have to reduce what you have in flight because you have to reduce the memory footprint, so that you have to find a trade-off. Okay, then I want to come to common efforts, and here I want to mention the CERN Next Generation Trigger project, which is effort by all the experiments, well, mostly Atlas and CMS, but Alice and LHCb have joined recently to do development for both software and hardware for the HL-LHC. And there are different work packages, experiment-specific and generic ones, and examples would be for efficient data structures and for machine learning interfaces. Then there's ACTS, which is the common tracking framework developed at CERN, experiment independent, but it was basically started in some sense by Atlas and will be used by Atlas for HL-LHC, but it's also used by others. For instance, Alice will do it for Run 5, and Phaser and S-Phoenix will also use it. There are ongoing efforts to port it to GPUs, which is called TrackCC. You see some plot running on GPU here. And then beyond processing, there is, for instance, DC24, which is a data transfer challenge, which was done by all the LHC experiments. And then, of course, there's all the usual suspects of generic software, which is used by everyone, so Giant, Root, and the generators. And they are all looking into GPUs, and experiments are trying to adapt it. So, for instance, Atlas and LHCb are looking into that a lot. And like keywords here would be adapt and accelerators for Giant. Then there's optics and Mitsube for photons, and we have even more. And okay, this brings me a bit to simulation. So what you see here is two plots by CMS and by Atlas showing the evolution of the simulation performance over the last years, and both of them have achieved roughly a factor 2 speed up over the last years, which is quite nice, and this is full simulation. However, it's in some sense incremental, so it's not that order of magnitude jump that we would like to have, and so therefore everyone is working on fast sim as well, or to use machine learning, or to use GPUs as was shown on the last slide. Then, yeah, some more topics. So we are not the main customer of the large IT companies. These are for machine learnings and for HPC centers. So we basically have to follow the path that they pave with the hardware that they release. So we basically have to adapt from using CPU plus GPU heterogeneous farms that we have today to something like NVIDIA Grace Hopper or Apple M3, which is ARM-based. So for ARM, we're actually in a good situation. So Atlas has already announced that they will support ARM pledges next year. All the other experiments can compile and run their code on ARM, but they are still in the validation phase, but I think they will converge sometime soon. Then one topic is open data. So the releases by Atlas and CMS are already out. LHCb has released the full Run 1 data set, and they have released the ntuple wizard, which is a nice tool for all the external users to access this data. And Alice is a bit behind here, and the problem is actually data format, because Alice has switched from event-based format to time-frame-based format in Run 3, and this has to be exposed here. And here I want to really emphasize that data formats is a general problem, because if we look at LHC, then we will have a time span of 30 years from 1.1 to end of HL-LHC, and we want to process the legacy data with HL-LHC software. So this is really difficult to maintain. And then, yeah, one topic is storage. And this is more critical actually for analysis than for reconstruction. And the critical thing is actually also just reading the data from tape or from disk fast enough. So there's a lot of work ongoing to improve the analysis. So the most important keywords here are analysis facilities. So that is the idea to basically have the data local on site. Of course, it's still made available to the outside, but the local access basically provides or guarantees fast access. And then you have all the tools on site for both distributed and interactive analysis. The data formats are switching to some more column-based formats. So examples would be root RN tuple or Apache Arrow. And the idea is that this can be, well, it can be stored in a more efficient way, and it's also faster at processing, particularly for something like SIMD processors. And then, yeah, for the analysis frameworks, I want to highlight a bit what Alice has done for Run 3. So Alice has switched to what is called Hyperloop. And Hyperloop is a framework for web-based composition of analysis trains. So multiple users can submit multiple tasks, and then they are grouped into a train. And the train will run either in the analysis facility or on the grid, and will access the data only once while processing all the tasks. And this is supervised by central operators. And what is really nice is that they provide 24/5 support with 4 institutes running in in different time zones. So you have really fast turnaround time and fair usage policies. And this is quite efficient. So in the last half of a year, 7,500 CPU years of grid were consumed, processing 400 petabytes of input data. And with that, they were able to process more data than with the old framework in the same time, even though the old framework was using 3 times as much CPU resources. Okay, my last topic then is machine learning, and I will be really brief because there's also a talk by Xavier, or there should be a talk by Xavier on machine learning. What I want to say is that machine learning, it started to be used in analysis for all the LHC experiments, and now it has become pervasive everywhere. So it's used in, well, first by all experiments, and then it's used simulation, reconstruction, calibration, and analysis. And there's a couple of topics that is certainly not a complete list, but it's used for fast simulation, it's used for calibration, it's used by for clustering by all the experiments. And there are new topics like using large language models, for instance, in Chatlas at Atlas, and it's used for tracking. And particularly, I want to mention the GNN for ATK at Atlas and the GNN tracking at LHCb that was presented at this conference. And the challenging thing, I think, recently has become that the models become larger and larger, and it's challenging for us to actually use, train, and manage them. And here, the CERN Next-Gen Trigger project comes into play that I mentioned earlier, because this has work packages that actually look at machine learning. So first at how to integrate the inferencing in our frameworks, and then also to purchase hardware that can be used for development or for training for all the experiments. Okay, with this I come to the conclusion. So yeah, I think the HL LHC upgrades, or the upgrades for ALICE and LHCb, they are really challenging from the compute side and from the storage side. And we have to make sure that we have efficient online processing to compress the data and to trigger efficiently. ALICE and LHCb have gone in the direction to completely go away with the hardware trigger. They do everything in software, and particularly they do everything on GPUs. And CMS is using GPUs today, and Atlas will probably do for HL-LHC. In offline reconstruction, it's a bit more complicated because GPUs is not so easy to use, but ALICE is already doing it for 60% of the workload, and they aim for even more in the future. And today they have this 2.5 times speed up that I mentioned. And on top of the offline reconstruction, I think it's even more difficult for analysis, but there are some ongoing projects, but nothing that can be used so far. Yeah, there were all the studies that I mentioned to use fast simulation and machine learning for analysis. Then 2 topics that I want to mention because they were emphasized by all 4 experiments when I asked is the evolution of the data model, which should be friendly for the analysis, but also friendly for accelerators to be ported to GPUs, for instance. And the multithreading to increase the processing throughput and to reduce the memory footprint. And for ML, I can only say what was on the last slide, because it's really brief, and I don't have much time, that we have no pervasive ML usage everywhere, but what we are lacking is handling of the large models and turnkey systems for seamless integration of integrating them in our frameworks. Thanks for the attention.
Thank you, David. And I can just clarify the machine learning talk that you cited has been rescheduled for tomorrow, so it will take place. Now I can open the floor for questions. Please make yourself visible. I can see one up here, maybe.
Hello. I would like to know what are the requirements regarding network infrastructures for these kind of systems?
You mean for the online systems that I mentioned? Or for what?
Yes, like the HPC systems, like what are the network requirements, like bandwidth and those?
So I can mostly tell for ALICE because that's what I know. And here the network requirement is not so hard. I mean, if you have a decent Ethernet or InfiniBand at 100 gigabit, that's more than we need because we are still limited by the processing speed, not by the bandwidth at that level.
Okay, then we'll take a question over here.
Thank you for the talk. I'm from LHCb, so I would have just at first slight comment about this full online computing on GPUs. Unfortunately, so far it's just HRT1 part. HRT2 part is still fully CPU-based.
Yes.
Yeah, so for order selection and so on, it's, well, final selection is based on CPUs. But talking about GPUs, well, we see that's practically one of the main way forward. Yeah, so all experiments will have to go to GPUs in some sense. But then there is a question of manpower because, well, writing a proper code on GPU is pretty difficult, and make it really fast and efficient is even more difficult. But let's say, from the analysis point of view, more and more people are switching from C++ just to Python. So what is your opinion about how to keep enough developers working with this type of programming languages, and even like make sure that those people are kept within the collaborations and properly promoted?
Okay, that's a good question. I think first you're right for analysis because people are moving to Python, and that is why I was not even talking about analysis usage for GPUs, because there were some ideas, but I think it never converged. I think for finding or for using GPUs, an important thing is what Alice has shown here is that you have to find some hotspot that you offload, and you don't have to run everything on GPU, because let's say we have the GPU farm, it has 80% of the compute power on the GPU. If we manage to do 80% on the GPU, actually the processors are still there to do the rest, so you don't have to offload everything. For the manpower, I think what you say is absolutely critical, so the experiments have to make sure that they have a long-term plan to keep the people who developed the GPU code in order to maintain it, at least some of that. I mean, in some sense, for instance, wait, so this, I didn't mention it, but it's written here. This was, I mean, this work, which was presented at LECP, is actually a master student at Alice. So he was just using the framework, he was porting the code, and it's really nice that within 6 months he could actually provide 1.5 to 5% improvement to the global Alice offline performance. And I think, in some sense, if you have a core group of maintainers that can do this, you can have people that develop individual algorithms that run on GPU written in some generic way, which is then maintained by other people. So that is also possible. But you have to have a core group, and you have to have a continuous plan to have the core group employed by your experiments. Otherwise, you will run into problems.
Do we have another question? Yeah, over here.
Jiří Chudoba, Institute of Physics, Prague. Thank you for your excellent overview and as well about mentioning GPU usage. Now we are trying to use more and more supercomputers. So do you think in the future we as experiments should evolve our frameworks to be able to use those supercomputers, or vice versa, that those supercomputers should be built according to our needs? What is your opinion?
I think that supercomputers are built to our needs is not an option if we don't build them ourselves. So if we want to use them, we have to adopt our frameworks or software to run on them. And for instance, Alice is doing this. It's actually, no, it's written on this slide. So for instance, Alice is looking into running at NERSC, which is a supercomputing site in the US. They have NVIDIA GPUs. So you have to make sure that your software is just generic enough to accommodate for that. I mean, there are some requirements. For instance, the site should have access to CVMFS to load the software. I think on that level you can negotiate, but yeah, then it's you who has to adapt.
Do we have another question? Yeah, we do here.
Yeah, that's a follow-up. Very nice presentation, really a good summary of what's going on. So as a follow-up for this question, not everything runs on the GPU, as you said, and the supercomputers, well, they're all based on GPUs, right? So how efficiently can you actually run at a supercomputer, meaning that you really use the resources that are there? Could you say something about that?
So I can tell again for Alice. So the Alice EPN farm has 90% of the compute power in the GPUs. So by offloading 60% of the workload to the GPUs, you will actually still be CPU bound, and you will have a GPU load of around 40%. In this optimistic scenario, when you offload 80%, you will still be CPU bound, but you will have a GPU load of around 60% or so. So in order to be really equal, you would need to offload 90%, which I think Alice will not manage. But then it's also an extreme scenario with 90% of the compute power in the GPUs. If you look at other sites, maybe they have 80%, and then with this approach here, Alice could even fully use it. And one should also mention, like, even if the GPUs are not fully used, if 80% is offloaded and there is a speed up of 5x, that's still enormous. And okay, we could get 10x speed up if we would do even better, but I think we should try to start with 5x and then we can improve.
Okay, let's thank David again.
Okay, and our next speaker will talk about detector developments, which are critical for experiments in particle and nuclear physics, and it will be Petra Merkel, and she is from Fermilab.
Thanks, Dimitri. I hope you can hear me well. So I'm not even going to try to summarize the beautiful talks from the parallel sessions, because this is a very wide field, of course. I could talk for hours. Instead, I decided to give you a very personal selection of a few key technology challenges we're currently addressing through R&D in just these few areas here. So now I'll start with collider detectors. And there I really would like to talk about silicon. Silicon detectors really have become ubiquitous. They're the workhorse of the collider experiments these days. They've grown from the initial just a few vertexing layers to really everything. Now we are building full silicon trackers, timing layers even, and even high granularity calorimeters in the near future. And one topic that I think is really important for the near future, and is already going on now in Alice, that I'm showing here with the ITS3 that's currently being developed and built, it's basically moving to CMOS maps, so monolithic active pixel sensors. And the advantage here is that you can achieve truly cylindrical vertexing, tracking, and even calorimetry with, in this case, near-transparent, for near-transparent vertex detector. The key technologies here to achieve are these sensor stitching and the thinning down to about 50 micron of the silicon, so it becomes bendable like paper. And you can basically bend the layers into the shape you want. You're not bound anymore by these small modules that you then have to tile together into your layers or disks. And so the way this is being done now for Alice, for example, as shown here, they're using these 30mm wafer scale CMOS maps. So that's basically one 12-inch wafer, 30 centimeters. And they're making one single sensor out of a whole wafer. And that is being done by stitching together these individual chips. The advantage here is, so I said already, the thin, so you can really lower your material budget, which is very important, especially on the innermost layers. The power intensity also goes down, which means you don't need a lot of cooling, which again would add mass if you had more cooling. And mechanically, you can also hold these in place with very thin carbon foam, for example. So that, again, adds very little mass. And in case of the ITS3, the plan is to use air cooling. So again, no mass, basically. You don't have any cooling pipes or cooling liquid that you need to pump through there. So the result is a very low, extremely low material budget. You can see here on the bottom plots, for example, the evolution from the current one, the ITS2, where you see this is the mass distribution, the material budget across phi, and in yellow you have the silicon, and everything else is basically all the support and the cooling. While for the ITS3, this is it. So you have zooming in here, that's the whole plot, and the silicon is just down here, it's about the same, but you have basically nothing else but the silicon. So this is becoming what we are calling a near massless or transparent tracker. A word about the stitching. So this is normally in a CMOS process, you're bound by this reticle size, which you see here. This is basically what industry does. But what you can do with the stitching is that you take your wafer, and then you take individual components on your reticle. That can be, for example, here, this is individual pixel masks, or you have a periphery here. And you just, during the photolithography process, you put them in certain places on your sensor. In this case, you could put this one here, 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 here. And then you take the pixel mask, and you can repeat it over and over and over. And this way, basically, you have one large sensor that's contiguous. And then by thinning it down, like I said before, to 50 micron or so, you can bend it. You can see down here, this is one large sensor that is bent into the right radius, and then eventually wire bonded to the front-end electronics here, furthermore, to give power and readout and so on. And the performance has now been proven in R&D, and it's showing to be excellent. So it's comparable really to keeping the same sensor flat. For example, the spatial resolution has been shown to be about 5 micron, and with excellent hit-finding efficiency. And this is now still in the R&D phase, but the detector is about to be built. Another evolution for the silicon detectors is certainly on the ASICs, so the application-specific integrated circuits. Our detectors are becoming more and more intelligent, and we need to put more functionality on the detector directly, including machine learning. And you can see, for example, here the example of the RD53, which was the common development between Atlas and CMS for the high Lumi pixel detector upgrades. And there's more going into the chip from storage, power distribution, clock recovery, and of course the readout of all the pixels in this case. And the more intelligence you put in here, the more power you need, of course. Again, the more power you need, the more cooling and mass and so on. But also with at future Higgs factories, for example, you will encounter enormous data rates and data volumes. And one way to tackle this is to put more intelligence on the detector directly. And for example, one idea here is to put machine learning on the ASIC and make physics-motivated data reduction already on the detector itself. So within a single module, you can already cut on things like incident angle, PT of the particles, even the hit position, their uncertainty, and so on. And there, of course, with all this silicon detector development, both the sensor and the chips, there's a lot of synergies also with neutrino and dark matter detectors, as well as medical imaging. So this is a sort of theme that I'm trying to point out, where there's synergies in our field that we really need to pay attention to and try to pursue. So next one up here are dark matter detectors, and Jocelyn already did a very nice job earlier to show you a lot of the different detectors that are involved in order to cover, for example, these 50 orders of magnitude in dark matter mass that we need to search through in order to hopefully one day soon find dark matter. And there are all sorts of different technologies that are needed and stitched together basically in X here in order to cover the whole phase space. And I just want to point out a few of them, starting with sub-GeV dark matter, direct detection using CCD. So these are scientific charge-coupled devices, and particularly I want to talk about what we call skipper CCDs. So if you know how a CCD works, it's basically an array of pixels that, similar to the collider detector, again, you have ionizing particles passing through. They create ionizing charge that then drifts to the electrodes and gets read out. What you can do in a skipper CCD is that you move from the sense node, you can move the charge you've just read out back to one of the pixels, basically, and then read it out again in an independent way. This way, you get much more precise on the charge you read, but you do not accumulate extra noise. So this way, you can really increase your signal-to-noise almost arbitrarily. And this way, at the cost of the readout time, basically, because the more often you do this, the longer it takes. But you can get to sub-electron or sub-photon noise with these detectors. And this is extremely crucial for these very low threshold needs of the sub-GeV dark matter detectors. Of course, as I mentioned, this is slow, so this will not work, for example, in a collider detector like this. And there are some applications where you also want to speed this up. And there's R&D going on, of course, into this direction. For example, you can think of regional readout or energy-dependent readout. So depending on the first data you collect, you reprogram your sensor to only read out certain areas. And one of that examples is shown here. So this is on the top here. This is one CCD sensor, and you can see the word smart skipper spelled out here. And everything that's in this blue-greenish, this is just read out once. So that's your standard noise in this case. So that's these data here, these channels, and that's fit to about 3 electron of noise, which is already pretty good. But then these white and dark blue pixels here, that's these. So you can see there's a lot of, most of them have 0 charge, so that's the white. And then you can see pixels that have 1 electron or 2 electrons and so on. And you can fit them, and you can clearly see, so these areas were defined by the mask, obviously, to read out many times, in this case, 500. And you get to a noise of 0.13 electrons. So you can think of many applications where this could be really a game changer. And you can see here on the bottom, this is current exclusion plots in sub-GeV dark matter. And you can see current limits from some of these experiments where they use only a few gram, and even just at the laboratory depth and not even very deep underground. And then you can see these are the currently planned and under construction experiments in this kind of technology where we move up really to many kilograms and go deep underground. And you can see here in orange, this is an area that's motivated by theory models. And you can see this is extremely competitive in this mass range. Another mass range, of course, is, as we heard before already, axions, and they were at least a very prominent model that we try to pursue. And that's this mass range here, and you've seen all these plots, exclusion plots, trying to get down to the models, and that each individual experiment sometimes only makes one single line in frequency or mass on this plot to exclude things or eventually find something. And you need many different experiments, even different technologies to really cover this whole phase space. And so typically, like these experiments you see here, so this is typically done with these cavities, where the cavity size is matched to the axion-Compton wavelength. And then the axion to photon conversion, the power of that is proportional to the volume of your detector. And that does not scale very well to the high masses or frequencies. And so we are looking there to do R&D to find new technologies, new ideas. And one of them is shown here. So here the idea is to convert the dark matter into photons and then count single photons with these very sensitive devices like the Skipper CCD that I showed before, but there are others like SNSPD or kits or bolometers, etc. So the idea is here that you have the axions interacting with a static magnetic field, very strong magnetic field, and then produce an oscillating parallel electric field in there in this free space. And if you put your detector in there, for example, in this case, the idea is to put this very shiny, very reflective, sort of inverted conical shape in there, and the photons that get created by the dark matter would be reflected twice and then onto a focal plane, and then up here you put your single photon sensitive counter. And that would be, for example, here is currently done in this R&D, which is called BRED or GigaBRED because it operates in the gigahertz frequency. So it's basically a broadband coaxial dish antenna. So that's this coaxial dish. And depending on what the dimensions of this and the kind of sensor you put on top, you can change your frequency in which you're sensitive to the dark matter. And in case of this GigaBRED, then you would, in this case, just cover this. And that's just with the prototype detector. So this is a potentially very powerful new idea with which we could span large areas at high mass here for the axions. Then going even further up in mass, of course, you have these large mass noble element detectors, either liquid xenon or liquid argon, and so on. Here, the name of the game is really to get larger and larger, because it's so unlikely that your dark matter interacts in the volume of your detector. In order to speed that up, you need to go as big as possible. But for example, on the liquid xenon side, the size is a bit of a problem, because xenon is quite rare. So the annual xenon supply needs to be boosted if we want to make this, the next generation of this, a reality. And what you typically do here in these detectors, you reconstruct both the scintillation light and also the ionization charge, and then you can reconstruct the XYZ position, basically. But basically, again, as I said, if you want to move to the next generation, you might scale up from something that's 7 ton right now of liquid xenon to something like 200. And that becomes a huge challenge. And again, also to point out again, lots of synergies here with neutrino detectors, large noble element detect TPCs there. So one piece of really cool blue sky R&D I would like to point out in this area is shown here. So this is really people thinking outside the sort of phase diagram box. This is a table showing, if you look currently at a 7-ton liquid xenon experiment, what the dominant backgrounds are. And this is all, this is lead and xenon 127 in this case, from radon decays. And these are things you could, for example, try to get rid of if you would not work with liquid xenon, but solid detector. So you would crystallize your xenon. And this is done currently on a very small prototype detector, where you have a 2-phase solid crystalline xenon and then a vapor phase. And here you could, for example, the radon would be excluded in this case. It would not be frozen in, while the lead would be frozen in, and you could handle it much easier than in the liquid phase. And I put a link here to a very interesting talk given at this CPAD workshop last year. And some preliminary results from there indicate that this actually might work. So this is, again, a very small prototype detector, and it's operated about 20 Kelvin below liquid xenon working point. But they find that scintillating light, for example, matches that. So in blue, you have that in the crystal, and in liquid, in orange in the liquid. So that looks pretty similar. And again, this is for then the drift time, for example. You see that this might actually be faster in the crystal. So that is something very promising that you might look into. The question is, of course, how could this be scaled up? But you might not have to scale up to the 20-ton, but maybe only to the 7-ton detector. But yeah, this is truly blue sky. This is really something new that we're pursuing. And then moving to neutrino detectors, and here I just would like to talk about one of, not the, but one of the Dune challenges, and that is really the readout and make that as precise as possible. We need to achieve something like 4 millimeter spatial resolution in a stadium-sized detector, something like 50,000 cubic meters of liquid argon. Or this would, if you did that at this size, that would correspond to something like 1 trillion spatial voxels or readout units. Usually, so traditionally, liquid argon TPCs use these 2D projective readout, so these wire planes, anodes and cathodes, and then you drift the charge and you read out the scintillation light, and then you reconstruct pretty slowly your image of the neutrino interaction. You can see this here as an example. So you have, so on top you have the traditional 2D projective readout of a neutrino interaction, and then on the bottom, that's the simulated interaction. You see that it does not reproduce it very precisely. While on the bottom, this is what you can, and it's not playing, it's animated, but it just turns around and shows to you from 3 dimensions. So you can really get to true 3D imaging by using pixelated readout. So that means you put pixelated basically readout boards all around your TPC and get continuous readout with 100% uptime. These are intrinsically sparse data because you really only read something out if it hits this 1 pixel. That leads to low data volume and also improved signal to background, and which again in turn leads to an enhanced low energy program if you can achieve these lower thresholds. And there's again pointing to an interesting lecture about this whole topic. But you can see just a few examples here, and there are multiple R&D collaborations that have been formed over the last few years that are trying to achieve this pixelated readout for Dune, both for the near and the far detector. And here on the bottom, you can see an example from the near detector. This is a high-intensity neutrino interaction event just after the beam. This is where the beam enters in the near detector. It's a huge mess, but you can see this is extremely fine information that you can have available by using this pixelated readout. All right, so I already reached my summary. So I just wanted to highlight here that there are many R&D challenges to enable science at future colliders with near-transparent or even very massive silicon detectors. If we talk about the calorimeters, there's a lot of R&D into different technologies that is needed because it's crucial to really comb through the whole 50 orders or so of magnitude to find dark matter. And then on the neutrino side, it's really crucial to lower the thresholds, especially on the charge, but also get the uptime and the efficiency to measure all the light in these very large detectors in order to reject as much background as possible and understand the nature of neutrinos. And in all of these, I wanted to point out that there are a lot of synergies across these different frontiers and across the different technologies. And I think it would be most efficient if we all work together on these. And that's the message.
Thank you, Petra.
Yeah.
But thank you for a nice talk. And we have time for a couple of questions. Please raise your hand. Interesting, look. This solid xenon, yes, so that's amazing. Yeah?
It's really blue sky. Who knows if it will work? But it looks promising.
Anyone? Don't see any hands. Looks like it's very clear, exciting talk. Yeah, so, okay, let's thank our speaker again for a wonderful presentation. Thank you, Petra.
Okay, now we'll continue with the special event, a lecture on the topic of quantum sensing in particle physics. So I'd like to welcome Michael Dozer.
Okay, so the format of this talk is slightly different from the others because I've been asked to give something that is more like a seminar rather than a presentation, which also means that I have way too much time, and I will try not to abuse your patience because I know that I'm standing between you and a party afterwards. So I've been asked to talk about quantum particle detectors and try to focus on applying quantum sensors to both high-energy physics and low-energy particle physics. Now, before talking about some examples in these different areas, I'd like to clarify what the terms mean or how I take them to be used, then talk about some particular examples of quantum sensors for low-energy particle physics, then give some ideas, some first results even, on using quantum sensors for high-energy particle physics, and then say a few words about the overall landscape, how this fits into the processes of detector R&D in the coming years. So first of all, here's what I mean by quantum sensors. For me, a quantum sensor is a system that will register a change of a quantum state that's caused by the interaction with an external system. For example, transitions between superconducting and normal conducting device, or the transition of an atom from one state to another, from an excitation level to another, or the change of a resonant frequency of a system in quantized manners. So these are highly sensitive and highly specific sensors for minute perturbations. And with that in mind, the definitions I'd like to use is that a quantum sensor is a device, the measurement, sensing capabilities of which are enabled by our ability to manipulate and or read out its quantum state. And because the commensurate energies are very low, you don't need much energy to get a quantum system to change from one state to another, unsurprisingly, quantum sensors are ideally matched to low-energy particle physics. However, and I hope I'll be able to convince you of that, they can also form natural elements of high-energy physics detectors, and I'll touch upon both areas. What I will not talk about, and this is probably, well, for a number of reasons, but mainly because there have not been that many good suggestions up to now, is how entanglement could be used as part of a quantum sensor and how to apply those to actual devices. You've seen this plot before. I'm going to use this as an example to explain why quantum sensors can be relevant in certain cases. So what you see here is the energy deposited in a detector by particles, and you saw this before as a part of a justification to look for dark matter, very light dark matter, where a nuclear recoil or electron recoil requires very sensitive devices. In fact, these devices up here, liquid, noble gas or bubble chamber detectors, or even ionization in semiconductor and insulators, will typically have band gaps of the order of an electron volt. So this is very good to detect relatively large energy deposits, but if you are trying to measure very low energy deposits, you're going to have to go to tailored materials, low gap materials with band gaps of the order of 10 to 100 millielectron volts, for example, gallium arsenide or sapphire, or even lower band gap devices, such as superfluids or superconductors, which have band gaps of the order of 1 millielectron volts or even lower. So basically what you have to have in mind is you have to think about what the goal is. Do you want to detect a MIP, or do you want to detect some minute sub-MIP energy deposit? For these very low energy deposits, you're going to need very low band gap materials, whereas for much higher or much lower particle masses, and for lower particle masses, you really have to think of these as very weak fields, other quantum sensing technologies are going to be more appropriate. And here's an overview of a number of quantum sensor technologies that are being used to look for dark matter candidates somewhere between 10 to the minus 22 and 10 to the 14 electron volts. And you can see that there are many, many different families of quantum sensors between quantum materials, qubits, exotic atoms, haloscopes, RF cavities, atomic molecular nuclear clocks, all the way up to very high mass devices, for example, optomechanical sensors. In this region here is the area that we're most familiar with as high-energy physicists, and I will talk more about those afterwards. But basically one has to put this into a larger framework. And this framework is the framework of the ECFA roadmap that was launched in 2020 with the goal of identifying which of these many, many families are most relevant to future particle physics detectors. And 6 families were identified as being particularly relevant. Those are the families of superconducting devices, transition-edge sensors, superconducting nanowires, cryoelectronics affiliated with those. Then the family of spin-based devices, such as nitrogen vacancy diamonds. Optical clocks, a very large family of ionic atomic molecular systems. Optomechanical sensors, where different modalities are coupled to each other, so optical to observe a mechanical perturbation. And then a very large family of engineering at the atomic level type materials, so 0-dimensional, 1-, 2-dimensional materials, metamaterials, and so on. And with these, the kinds of physics that one can do is to search for new physics beyond the standard model physics, to search for axions, axion-like particles, dark matter, non-dark matter, ultralight particles, to also test quantum mechanics, for example, to try to understand what causes the collapse of a wave function or what causes decoherence, to test fundamental symmetries or search, for example, for electric dipole moments. And this is going to be the second part of my presentation here, or my talk, development of new types of detectors. So let me first focus on the low energy particle physics, and there, out of these many different possibilities, I really have to select a very small set. This is a personal selection, and even there I can only give a ridiculously rapid overview of how these different devices will work. And so I'd like to say a few words about work that's going on right now on radio frequency cavities and cryodetectors for dark matter searches, field sensors, also for dark matter searches, atom interferometry clocks and networks to search for dark matter, but also to measure gravitational waves in a frequency range that is currently not accessible. And then a number of exotic systems, atomic, molecular, ionic systems, that allow one to test QED, but also to search for beyond the standard model physics, to be sensitive to gravity, to test fundamental symmetries, and also to search for dark matter. And in fact, I'd like to link in a few places further literature that builds up much further than I can cover in this talk here. So the first set of detectors I'd like to talk about are superconducting sensors, RF cavities in particular, and these are being used to detect axions, or axion-like particles. In particular, in the range around 10 to the minus 6 electron volts. So around these microelectron volts, RF cavities are very sensitive, and they have a figure of merit that is composed of the coupling constant of the axion to 2 photons. So this is how you normally detect it, for example, in a haloscope or in a helioscope, where one of the photons is the magnetic field of the magnet in which the axion converts to a photon. Then the square of the axion mass, the 4th power of the magnetic field in which this RF cavity is sitting, the square of the volume of the cavity, and then the inverse square of its temperature. And in order to expand this very narrow window that is currently being explored by RF cavities, you'd like to go to lower masses, where you saw in the different plots already that one would like to reach the standard model axion prediction, the QCD axion prediction. In order to go to lower masses, if the mass goes down and you want to keep the figure of merit constant, you're going to have to change some of these constants here accordingly. For example, if the mass goes down and you keep the magnetic field at the value, the maximal value that you can do, then you have to scale up the volume quadratically, which very rapidly runs you into trouble. Now, if you want to avoid that, and this is an approach that's being pursued by several groups, at DAISY, at CERN, also at SLAC, where the idea comes from, you can try to, instead of having a single mode cavity, have a multi-mode cavity, a dual mode cavity, where you have a pump mode, omega 0, and a signal mode, omega 1, and the two are coupled to each other through the axion. This is a little bit like an atomic system, where you have an energy level, a second energy level, and you induce a transition between one and the other. Now, in order to be clear on any signal that you see in the signal mode, the two modes have to be very well separated, so you have to have very high quality factors. Here, the dark SRF collaboration has managed to build cavities with quality factors of the order of 10 to the 10. So you can very well separate the two modes from each other. But you'd also like to be able to tune these modes. If you just build a device with 2 modes, that will be perfect for a specific axion mass. If you want to scan across this whole mass range of axions, you're going to have to be able to tune the mass gap between these 2 resonant modes. And so this means you have to change the frequency, the modes of the resonator or of this cavity. And that means either mechanically deforming this device here at the level of nanometers, as was originally proposed here, or by tuning the field, by changing the properties, the electrical properties on the surface, for example, in superconducting RF cavities, or through some other means. But if you want to go even lower, that's not going to be enough. You're going to have to look at other modes of axion interactions with your detector, going into the very, very low mass range. And this is a range where the axion is no longer a particle. One really has to think of this as a field. And so here are 2 examples of what one would do at these very low axion mass ranges to detect the axion. You can think of it as trying to pick up a very weak electric signal in a tunable resonator that you then couple to the outside world via squids or RF quantum up converters or cryoamplifiers. And you're basically going to scan along the resonant parameters of this circuit here to try to see if you have any power at any particular axion mass. You can also think of coupling the axion to spins. In the case of Casper, this is how one of the approaches is. You have a device here which has nuclear spins that in an external magnetic field are oriented, and an axion wind will get them to precess. And so you can pick up this precession signal in a squid pickup loop. You can do this either if the spin couples directly to the axion or if the spin couples to the axion gradient. And in both cases, you cover this very low mass range all the way down to the standard model, the QCD axion limit, this yellow band that you're trying to reach in these searches. You can also try to look for this not only in a single detector, but in coupled detectors, using networks of individual devices placed around the globe to look for coherent signals that traverse multiple detectors at the same time. You can think of looking for oscillations, you can think of looking for fast transients, and you can think of looking for slow drifts in, for example, fundamental constants or caused by axions in different locations. So this means you can be sensitive to dark matter topological defects going through the Earth. You can also use, instead of the kinds of magnetometers that I just mentioned before, atomic clocks that are sited in different places of the globe. So for example, here's an image of the optical fiber network that is currently being put together across Europe. There are many gaps still in here, but once you have a coherent network, you can compare clocks in southern Italy with those in France, with those in Norway, Germany, France, and Poland, and see if you find differences that are due to these kinds of signals here. So that allows you to look for very light scalar and pseudoscalar dark matter candidates over many, many orders of magnitude. You can also try to take this into space, and this is the idea of the ion interferometer, which is currently at the level of setups of about a cubic meter, several of which are placed around the UK, trying to go after very light axion masses, but also into gravitational waves in a frequency range that's not currently visible. This standardization of 1 meter cubic atom interferometers is now in the stage where it's scaling up to larger atom interferometers of the order of 10 to 100 meters. For example, the MAGIS device at Fermilab is trying to go to 100 meters. ION is exploring the 10 to 100 meter scale, possibly also at CERN, where basically what you need is a vertical shaft of a length of somewhere between 100 and several hundred meters. And of course, cryogenics, vacuum, and so on. The ultimate goal, though, is to go into space with these, and there what you want to have is a standardized technology that is reliable, robust, and that you can work with. And this is what, for example, the ACES satellite will try to establish. as well as the Pathfinder technology developed missions, with the idea that on a timescale of about 20 years from now, you have networks of atom interferometers in space, either the ICHEP or the ION satellite missions, which allow you then to be sensitive to a frequency range between those of LIGO and LISA for gravitational waves. Let me take a step back. I mentioned radio frequency cavities. In fact, some of the experiments working with ions, or actually individual particles, such as the BASE collaboration, where a penning trap is sited inside a very powerful solenoidal magnet, is also able to detect axions in a very, very narrow band of around 3 nanoelectron volts, but where relatively straightforward improvements to their device, slightly stronger magnetic fields, better electronics, slightly longer measurement times, will allow them to map out this whole new range of parameter space. And this is for an experiment that is actually trying to measure the fundamental properties of protons and antiprotons as a test of CPT, charge, mass, magnetic moment. And in fact, in these penning traps, one can do many, many measurements. One of the nicer things one can do in penning traps is to work with trapped ions, and in particular, highly charged ions. Any ion in a penning trap will undergo multiple motions, axial motion in the penning trap itself, the electric field being a harmonic potential along the axis, and a cyclotron and magnetron motion due to the magnetic field in which this penning trap is embedded. And the nice thing is that any of these frequencies that one wants to study, or the properties of the ion, of the highly charged ion, actually scale very nicely with the nuclear charge Z. The binding energy of the electron, of the remaining electrons in the highly charged ion, scale as the square of the charge. The hyperfine splitting is the cube, QED effects as the 4th power of the charge, but the sensitivity to external electric fields via Stark shifts only scales as the inverse 6th power of the nuclear charge. So one has a very nice, very precise measurement of very small effects, and one is very insensitive to perturbations. And an example of what one can do, for example, in highly charged argon, so this argon with 13 electrons having been removed, whose level structure is very similar to that of boron, this 13 plus charge shifts the energy levels, the transitions between the energy levels from the optical, so 250 nanometers for this transition, 654 micrometers for the hyperfine splitting, into the optical range, where one can now do hyperfine splitting optically at around 440 nanometers. So this means one can do precision measurements on highly charged ions and really test QED very, very precisely. And this can be taken further if one replaces the electron of such an highly charged ion by an antiproton, or has the electron in a highly excited state. One can use antiprotonic atoms to form the nucleus, the bare nucleus, which is then trapped, and to which one attaches an electron or an antiproton. In this case, not in the ground state, but in a Rydberg state, which means that one can not only do the hyperfine splitting spectroscopy of these states, but also the Rydberg transitions, which is now in an area where nuclear form factors play no role whatsoever anymore. And one can do this for electrons, for antiprotons, possibly also for muons and pions, which means one can test exotic couplings in an approach very similar to the spectroscopy of muonic atoms, and carry out new forms of CPT tests. For example, searches for an electric dipole moment of the antiproton in systems like these here, but also look for novel dark matter candidates, such as a 6-quark standard model candidate, which is a scalar QCD bound state consisting of 2U, 2D, 2S quarks with opposite spins, whose mass would have to be less than 2 times the mass of the lambda to protect it against weak decay, and which is completely compatible with astrophysical bounds and not excluded by prior searches. So we did a quick simulation as how to make this in antiprotonic helium atoms, which would produce this dark matter candidate at rest, recoiling against the K plus pi minus final state, which doesn't occur in the standard model. And one can go down to branching ratios, production rates of around 10 to the minus 9, with very modest tracking and particle identification requirements. So this is what I wanted to talk about for the low energy particle physics. Now I'd like to also mention how one could use quantum sensors at high energies, and this is less obvious because obviously the quantum transitions that we're relying on are individual transitions, whereas in a high-energy particle physics detector, you have many, many interactions. Ionization signals, scintillation, Cherenkov photons are all the result of many, many interactions between a particle and the bulk of the detector. So there are some ideas that require perhaps less a quantum sensor per se, but more the possibility of manipulating the system in advance, and that allow measurements or permit measurements that are more difficult to achieve otherwise. So these are improvements or suggestions for improvements rather than a radical new design. And I should warn you, these are very speculative. So, well, some of these are already being shown to work, others really are very speculative. And I'll talk about 4 different areas: low dimensional materials, so quantum dots mainly, quantum dots for calorimetry and quantum dots for tracking, leading to chromatic calorimetry and chromatic tracking. Quantum boosted DDX, where one manipulates atoms with lasers to create something like a Rydberg TPC. Quantum polarized helicity detection, where one again manipulates bulk materials like diamonds with lasers and microwaves to spin polarize them to produce helicity detectors, and then superconducting sensors, which can be used as millicharged trackers. So the first topic I'd like to talk about is the quantum dots. These are very small assemblies of 100 to a few hundred atoms, which have specific geometries, specific composition, specific sizes. And depending on the size of these quantum dots, the scintillation light that they emit changes. The smaller ones emit in the blue, the larger ones emit in the red. And if one illuminates these quantum dots with UV light as a proxy for charged particle interactions, one can see that they're very clean emission spectra. In fact, the emission spectra are so clean that the bandwidth of such an emission spectrum is around 20 nanometers. And the 20 nanometer width of, for example, the red emitter at 598 nanometer means that it's above the absorption edge, which means that once such a nanodot has scintillated, the other nanodots of the same type can no longer absorb the emitted wavelength of that scintillator, which means one can try to think about building something which relies on putting different sized nanodots at different points inside a calorimeter. So here's a sketch of what this would mean. You have multiple layers, each of them seeded with nanodots of different sizes inside a calorimeter. If a particle comes into this device, it will produce interactions. Here's a sketch of what the shower profile would look like. The surface of these areas here results in scintillation light of that particular color, so that if I end up here with this intensity spectrum, this chromatic intensity spectrum, this spectral intensity profile will allow me to measure how much energy was deposited at different points along the profile. So what I'm getting here is basically a chromatic shower profile measurement, while of course the integral is the overall energy deposited in the calorimeter, as is the case currently. So here's an example that was presented by a doctoral student, Devanshi Arora, at the Calor 24 conference in Japan a few months ago. This is a simulation, a Géant 4 simulation, of exactly such a device where one has red, yellow, green, blue emitters, either in the bulk or between other objects. Here's the simulation, and here's the outcome of the simulation. What this basically tells you is that for electrons of different energies, initially for low energy, most of the light is emitted in the front part, so you get mostly red light, whereas for high energy electrons, the shower extends over multiple blocks, so you start getting more green light, some blue light, and by measuring the ratio of the red to the green to the blue to the purple, you can actually get a chromatic energy measurement. Currently at about 20%, but this is a new way of measuring the energy deposited in here. It doesn't require the overall energy measurement, it just requires measuring the ratio of the colors of the light coming out. This was tested in a test set up by this student here, working with Etienne Daufray-Hillemans, where they basically approximated this device here by a yellow scintillator, then a lead tungstate block, a blue scintillator, a lead tungstate block, and then a purple scintillator. So particles with different energies would be expected to have different ratios of yellow to blue to purple light. And that's exactly what they see. So here's the prototype. It was put into a test beam of electrons at 100 GeV, pions at 100 GeV. The ratio of the yellow to the blue light is shown here for electrons, here for pions, and here the two are combined. And from this, you can see that chromatically, so just based on the mix of the colors, you get an 86% electron-pion discrimination. And this is really just a very rough prototype of what you'd like to try to build in the future. But these are just dumb scintillators. They don't actually do anything. You'd like to be able to play with them, to electronically amplify them, modulate them. And for that, you might want to work with nanodots, or quantum dots, made of gallium arsenide or indium arsenide. Depending on the mix, you'll get different devices. They emit the quantum wells at just close to the infrared edge, the quantum well dots at somewhat higher wavelengths, and the quantum dots themselves at around 1.3 to 1.5 micron. So these are the ones that are the most interesting. They have a fast decay time of a few nanoseconds, and this wavelength of about 1.5 micron is very close to the telecoms wavelength of 1.5 micron, which is the area where silicon turns transparent. So one might speculate at this point that it could be possible to build scintillating detectors inside a tracker and just shine this light through the tracker. The infrared light should pass through the silicon tracker and should be detectable via photodetectors outside the silicon. And it might even be possible to pattern the structure of the silicon in such a way that one forms lenses for infrared light. One concern is, of course, the radiation resistance of quantum dots. Here are some older measurements from about 20 years ago that show that up to fluences around 10 to the 12 protons per square centimeter, quantum dots are not really affected by radiation. Now, you could try to take the next step after that, which is to actually use these quantum dots inside a tracker itself, bury them, and give them the role of catching the electrons from the electron-hole pairs that are produced as a charged particle goes through the detector. So the electrons are trapped by the quantum dots. These then emit photoluminescence light. And this photoluminescence light has a long wavelength compared to the absorption edge of gallium arsenide, so it will just go through the medium. And if immediately adjoining the medium you have a photodetector, then you can measure this light that is produced by the charged particle. So this is, in a way, a chromatic tracker. You're using the light produced by a particle going through your tracker to identify the position and the energy lost by the tracker. And the nice thing about these kinds of quantum dots is that, like the other ones, because they're very small, they have very rapid decay times. So in the case of gallium arsenide, they have decay times that are shorter than a picosecond. And if you look at how much light they produce, actually, they are already right now competitive with the best scintillators that are on the market, with improvements that are being looked into by several projects that would make them the brightest scintillators compared to any of the other scintillators that we have. Now, that's for silicon trackers. I would like to say a few words about how to potentially manipulate the atoms of a TPC with light, with laser light. This is a typical TPC. You drift the electrons from a charged particle through the drift volume, and then in the amplification region, where there's a very strong electric field, these electrons shower. Basically, you collide them, you accelerate them, you collide them with atoms, they release other electrons, those also are accelerated, they shower, and so forth. This has the problem that you produce in this very strong electric field ions that will then drift backwards and could potentially pollute or poison the drift volume. So what you could do is to excite the atoms in this region here from the ground state to a highly excited state. What this does, if you can do this for a sufficiently large fraction of the atoms, is reduce the energy needed to ionize the atoms. So you get an avalanche that is feasible at lower accelerating gradients. These lower accelerating gradients will still produce the same number of electrons, but the ions that are produced will no longer be accelerated quite as dramatically and will no longer move back into the drift volume quite as rapidly. So this is one possible use of atomic physics manipulation of the gas of a TPC. Obviously, what you can do in here, in the amplification region, you can also do in the drift region, if you choose your frequencies well, to produce a higher effective DEDX by simply producing more electrons for the charged particle to release as it flies through the TPC drift volume. The last type of detector is a spin detector. The idea here is to try to polarize locally very small amounts of material. So these are nitrogen vacancy diamonds that can be polarized to approximately a per mil of the overall density of states or density of atoms in this volume here. And the idea is that if you can build planes of these devices that you then intercalate between a tracker, the spin-spin scattering inside here between the charged particle and the polarized medium itself might allow you then, by reconstructing the trajectory and the multiple scatters, the spin or the helicity of the original particle, which currently is only measurable by particles that decay, where you can do a full partial wave analysis of the particle. And the last detectors I'd like to quickly come to are superconducting detectors. In particular, nanowires, superconducting nanowire single photon detectors, which work by absorbing a photon where the superconductor is heated up locally. The current that is constantly flowing inside the conductor is forced into a smaller region, exceeding the critical current density here, and then completely heating up the nanowire locally. It takes a certain amount of time for that heat to diffuse back into the bulk, which is being cooled, and the nanowire to go back to its initial state. So this works for a single photon. You get a single voltage pulse like this, but it also should work for minimum ionizing particles. The nice thing about these devices is they're extremely sensitive. So this is the current sensitivity of around 100 millielectron volts deposited in 10 micron. The goal is to go to something like a sensitivity of 10 millielectron volts on a thicker detector. And that has to be compared with the amount of energy deposited by a MIP in the same thickness of around 20 keV, which means one has a millionfold sensitivity compared to the current MIP-sensitive detectors, which means that one could build stacks of these that would see millicharged or perhaps even microcharged particles as a track flying through a stack in a beam dump experiment where the only background, the muons, would have to be vetoed by having muon detectors that measure exactly which trajectories are muons. And one can use another characteristic of these nanowires, which is that they are extremely fast, to also think of using them in an environment, for example, an LHC collision point, to select out diffractive scattering of two protons, where one has then a superconducting tracker here, a superconducting tracker here. The timing has to correlate this track with this one, and these can be operated at around 20 Kelvin. So these are high TC superconducting nanowire detectors that are currently being worked on, and which may allow filtering out of this horrendous mess of charged particles those that correspond to two correlated particles flying off in opposite directions. And the last detector, and I really wanted to mention this one, is a qubit. Qubit, as currently being realized by the Google processors, or the quantum computer by Google, in form of transmons. So these are basically harmonic oscillators where one works on forming the harmonic oscillator in such a way that only these two states are addressable. There's only a transition between this state and this state. And in a 26 pixel device, the Google team has looked for the correlated noise, so simultaneous errors that are detected on each one of these qubits, and has realized that these here are actually locally clustered. So this is the pulse, the number of errors that you see, the number of errors in the different individual qubits, and one sees that they are localized, and this is interpreted as being caused by a cosmic ray passing through this qubit. So one can think of using qubits at some point for cosmic ray tracking. I should point out the timing is of the order of a second, so this is 100 millisecond decay time, and the pixel sizes right now are of the order of a millimeter, so we're not talking competition for pixel detectors quite yet, but it shows the sensitivity of these qubits in the future and the opportunities that working with quantum computers in direction of charged particle detecting offers. So the last is -1 minute, basically. I want to just give a very quick overview of the landscape. This is the ECFA roadmap that I mentioned before. These are the 6 families of quantum sensors that I indicated before. And this gives an idea of the ambition that might be reachable on a time scale of about 15 to 20 years and the difficulty of reaching these. A lot of R&D is needed, so implementing this roadmap was the topic of an effort in the last 2 years to try to come up with how to map these roadmap topics onto real work packages. This was done in 2023. A grassroots, ground-up process took place, building on what the roadmap had indicated as a possible interesting program. And at the end of last year, beginning of this year, we presented a version of a proposal with milestones and deliverables to the Detector R&D committee at CERN that was set up at the beginning of this year. And this process was approved by the research board. This collaboration, the DRD5 collaboration, was approved by the research board about a month ago. So this is basically the work packages that we have agreed on working on as a collaboration. This is the prototype of the structure of this collaboration, and this is the composition of the collaboration at this point in time. So since the moment we submitted a first draft proposal and the final proposal, approximately 100 institutes worldwide indicated their interest in being part of a R&D program on quantum sensors for particle physics. And this collaboration combines very diverse communities, including high-energy physics, of course, but also communities coming from atomic physics, superconducting devices, optomechanical sensors, and so on. Many novel developments that will benefit both quantum technologies and particle physics are being addressed in this process, and it's open to all interested parties, and it's free to join. And with that, I would like to thank you for your attention.
Thank you very much, Michael. Okay, we will open the floor for questions, so please make yourself visible if you have a question or comment. Yeah, we have one here. You see it's,
yeah, thanks for the nice seminar. Could you comment a bit more further about the connection between quantum sensors and the quantum computing field? In particular, some recent articles indicate quantum computing prefer quantum data rather than classical data. Will some of the quantum sensors be natural good candidates for producing quantum data? Thanks.
So the only link to quantum computers that I'm aware of at this point in time is this particular measurement, this particular experiment. Quantum computers are usually very small numbers of pixels. They are not yet at the level where you can have large arrays. The other technologies I mentioned are already much more mature in the sense that, for example, superconducting nanowire arrays, pixel arrays, are being used for satellite observations in the infrared in space. So those technologies are much more mature. It's more a question of bringing them into another field, the field of high-energy physics. For quantum computers, it's much, much earlier in the game. And understanding, for example, exactly this kind of link between how an individual qubit is sensitive to charged particles, this is something that is still more or less an open game. This is the only measurement that I'm aware of. There are several groups that are starting to think about doing measurements of combining, for example, a qubit array of qubits with charged particle trackers inside the cryostat. Going to a more complex understanding of what kind of data is being produced is perhaps a little bit too early at this point in time.
Okay, thank you.
We have a question on the right-hand side of the room.
Yes, so thank you for the very nice presentation. So I guess once we have to start, designing, deploying these kind of technologies, it will be important to be able to simulate their performance as we're currently able to do with current detector technologies. And I'm guessing that the toolkits that we have at the moment aren't going to be up to the job. The processes won't be in there. So I didn't notice in the work packages that developing simulation software for these technologies is part of it. I guess it's sort of implicit in each work package? Or?
It's implicit in most of the work packages, explicit in some of the work packages. For example, the work packages on atomic systems. There we have an explicit simulation sub-work package and deliverable, as well as in the nanodot work package, where one needs to refine the models of scintillators from this sort of continuous medium that Géant 4 would use, down to the molecular processes. But as you rightly point out, it's implicit in all of the other work packages as well. So it's needed. Definitely, I agree with that.
Any further questions? I see one here on the left-hand side of the room.
Hi, thank you. Sorry about my voice. I'm wondering, what exactly is CERN's involvement in the initiative? Like, is there a new group established? And are there going to be further positions in the future for PhD students and research scientists specifically in this field? Thank you.
Okay, so the answer to the last question is yes. I'm looking for a PhD student right now. Talk to me. CERN's involvement is started in 2020 with a 3-year quantum initiative, a prototypical quantum initiative, where we just tried to see whether some of the technologies that I talked about here have a potential. So that focused on the quantum dots, on monolayers of graphene, on control systems coming from atomic physics and seeing how to port them to high-energy physics. The current quantum technology initiative at CERN is a more ambitious program. It's a 5-year program this time. We're focusing on the superconducting detectors for charged particles, but also for X-rays, in exotic atoms, in milli-charged particle searches, and so on. The production of exotic ions, and the production or the building of multi-mode RF cavities. So all of these now build on expertise and technologies that are available at CERN, but also try to do this by connecting to outside institutes, which was not the case in the first quantum initiative. But on an overall scale, one has to say this is still a relatively modest effort. And the only way that this R&D program, the DRD5 program, can happen is if we can federate efforts that are happening around the world, often duplicating themselves, and the goal here is to try to bring together expertise, to bring together resources, and to bring together infrastructure that all these different groups need and have. And if one looks at the proposal that I flashed the link to somewhere, it basically tries to provide relatively soft milestones and deliverables in the sense of agreements between groups, trying to get them to work together.
Thank you.
I think there's time for a final question, if there is one. Where is it? Directed to the right-hand side of the room.
Hi, thank you very much for the talk. I'm interested in the stuff about the qubits, and I appreciate that this, as you said, is quite early on in terms of being developed, but you mentioned that a couple of groups are working on using qubits, and is that all superconducting qubits? Because there are a lot of different ways to use qubits, and in fact, quantum dots and the nitrogen valency centers, they can both be treated as qubits as well. So is all of the current research on superconducting qubits, and if so, why?
So as far as I know, the only ones that are being used right now are indeed the superconducting qubits, the transmons, mainly for 2 reasons. They're easier to work with for many groups. Many groups have the technology to work with single transmons or coupled transmons. But also because the quantum computers that are being worked on or being developed really rely mainly on that, are focusing on that direction. I'm not aware of many groups working on nitrogen vacancy diamond-based quantum computers where you still need to scale up at some level, just like with ions. So with ions, I know that you can couple 10, 20, 30 ions with each other, but it's not obvious how to scale this up to hundreds or thousands. With the superconducting qubits, it's maybe a little bit easier to think of scaling this up. And I think that's the main reason why most of the focus has been on that. And the only groups I'm aware of, indeed, are the ones working with transmons at this point in time. That's not to say that I wouldn't love to try this also with nitrogen vacancy diamonds or ions, for example, in a test beam.
Okay, thanks. We'll close the discussion here. So let's thank Michael again for the excellent seminar. And this brings the final session of today to a close, so let's thank all of the speakers of this session. And that's the end of the session today. The conference program continues with the panel on future of particle physics and also the party.